We are going to take a look at the concept of a sampling distribution in this video. We know a lot about some of the words in this title. We know a lot about sampling. We have looked at different sampling techniques. We understand that a sample is a small group chosen out of a population, and we know different sampling techniques. A simple random sample would be our best technique. We also know a lot about a distribution. We looked at probability distributions. We know their characteristics. We know that a distribution has to represent all the different possible outcomes, the probabilities of all of those outcomes. So we're going to put these two concepts, the concept of a sample and the concept of a distribution, together to create a sampling distribution. I have here the definition of a sampling distribution. And the definition is kind of confusing, so I drew a picture to help illustrate the definition. So it is a sampling distribution. So here I have the population in this big oval, and I am pulling different samples from that population. Now, I have to have, according to the definition, a specific sample size, and it has a lowercase n. So when I pool the different samples, they all have to be the same size. And for our purposes, we'll just make up a size, say n equals 10. So we pool from the population a sample of size 10. And then we pull from the population a new sample, size 10. And we repeat it, and we get a third sample, size 10. And according to the definition, we have to have all possible samples. So this dot, dot, dot means that we're going to continue doing this until we get all possible samples of size 10. Now, remember a few details. Back here with our population, the number of people in the population would be a capital letter N, whereas for each sample, we use the lowercase n. For the population, we could calculate the mean, and we'd use mu. We could calculate the variation, and we'd use the Greek letter. We could calculate a proportion. I'll talk more about that in a bit. Let's talk about means for the time being. When I have the sample with n equals 10, I can calculate the mean of that sample. A sample mean is x bar, and it's our first sample, so I'll use the subscript 1. Then I can calculate the mean of the second sample, the mean of the third sample. Eventually, remember there's all these that aren't represented that are just here, it's the dot, dot, dot. I would calculate the mean for the next to last sample. And I'd calculate the mean for the very last sample, which we called n. Now, I have all of these sample means, and so this is where the distribution comes in. I could list the sample means, and I could take the mean of the sample means. These sample means are my new set of data, and they would be called my sampling distribution. The mean of those sample means should come very close to the actual population mean. Let's take a look at another example. So again, I have a fresh population. Let's pretend that it is the numbers 1 to 100. For those numbers, I could calculate the mean. So if I add up all the numbers 1 to 100, I get 5,050. Divide that by 100 numbers, and I get the mean of that is 50.5. Then I could start my sampling technique. Say that I wanted to pick samples of size 20. So every single sample has to be size 20. And to get a true distribution, I have to do every single sample that exists of n equals 20. So I could actually calculate that, but it would be a whole lot of samples to get all possible samples of size 20. And in each case, I would calculate the mean. And so I'd take the mean here, and we call that sample mean 1, sample mean 2, sample mean 3, sample mean m, and sample mean n. All of these sample means would actually be close to the 50.5. And if I take the average of all those sample means, the mean of the sample means, it would be very, very close, if not exactly, the 50.5. So all of these means end up estimating that true population mean. Now, I have to note here that each of these samples were done with replacement. So if I pick the number 1, I put number 1 back in. I replace it. The reason why we have that with replacement is because then each event of picking a sample is independent. And that makes our calculations a whole lot easier to work with independent events. We will also remember from chapter 4, when we worked with probability, that when we have a large population and we're only pulling a very small sample, that having replacement or no replacement made no significant difference. You might recall the 5% guideline for cumbersome calculations because there was no significant difference if we used replacement or not. So since real life, most of our populations are huge and our samples are small, we will do everything with replacement to make our calculations easier. Let's look at one more example before we leave this concept of a sampling distribution. So I cleared my slate again. This time we're going to use a proportion. Proportions are mentioned up here in the definition, but we haven't used them extensively. A proportion is just a percent written as a decimal. Let's use the same example we did in the previous problem. So our population is the numbers 1 to 100. P, our proportion, is numbers less than or equal to 25. We would have 25 numbers less than or equal to 25 out of the 100 total. So P for this population is equal to 0.25. The proportion that is less than or equal to 25. So again, we'll go through and sample. Let's just have samples of 10 this time. So we'll pull 10 numbers, we'll replace them, and so that we have independent events. And then for each sample, we'll calculate the proportion of that sample that is less than 25. We'll call that P hat with a little hat on top of it. And for our first sample, the proportion P hat. For our second sample, P hat. For our third sample, we'll do this the whole way for all the possible samples there would be. And then what we would do is we'd take the average of all of these proportions, and that average proportion would take us back to a great estimate of the proportion for the entire population.